Check it out now, y'all.
nanoHUB-U, online instruction.
All right, welcome to the nanoHUB-U course, Thermal Energy at the Nanoscale. We are in the last lecture of the course. This is the Week 5 wrap-up lecture, and this week was about carrier scattering and transmission. And just to remind you, our general approach and framework for this course had us looking at integrals such as those shown on this page, where we're really studying term by term the number of modes, that's M, the transmission function, that's a big topic for this week, the energy of the carriers, and then if we're looking at conductance, then we're talking about a temperature derivative of the distribution function, that's either Bose-Einstein for phonons or Fermi-Dirac for electrons. And then we do that whole integral either in frequency space or energy space. And we do that for a particular arrangement. That's where we have a hot reservoir and a cold reservoir connected by a device. And so this week we started out with a very simple transmission model, and we said that the transmission function to first order should look something like what we show here. The mean free path, that's capital lambda, divided by the length of the device, and then we realized that we'll have to do something with the denominator. We added a term, the mean free path in the denominator, so that we could handle ballistic transport properly. So that corrected model does the right things. It says that as the device shrinks down to nothing, basically length of 0, we get a transmission function of 1. And then if we have a very long device where we have diffusive transport, then the transmission function is really the ratio of the mean free path to the length of the device. And so from that, we recalled back to our simple relationship for thermal conductivity based on kinetic theory. That's where we had a constant mean free path, and we're still kind of assuming that so far here. And we said that thermal conductivity just from kinetic principles would be the product of the group velocity, the mean free path, and the specific heat with a prefactor of 1/3. And if we actually apply that simple scattering model using the Landauer approach, we found that indeed we get something very similar to, in fact, it's the same within a constant. It's a product of velocity, mean free path, and then the integral that remains is the specific heat. So the Landauer theory does revert back to or give us back the kinetic theory result if we have this very simple transmission function model. And so that should be somewhat reassuring that we're on the right track here. We then started to get a little bit more complicated and said, well, let's talk about what this mean free path might look like. And we're going to talk more, we ended up kind of converting from discussing mean free path and turning that into the scattering rate, where really the scattering rate is just the group velocity divided by the mean free path. And so here we have a boundary scattering problem where we have some boundaries that confine the carriers inside of a material, and we're interested in the long or the continuum direction. And so we could have a lot of different shapes. We need to come up with some factor L that characterizes the confining length scales, and that's for a rectangular cross-section. The L that's shown here works well. And then this factor F is one of these engineering fitting parameters that depends a little bit on the geometry and more so on the smoothness of the boundary. Because what happens is if you had a specular boundary, that means that a carrier, when it hits the boundary, it reflects like a mirror. In that case, heat flow in the direction of interest here, that's the direction of the red arrow, would not be impeded at all. And so we wouldn't want to count that as a contributor to thermal resistance or an impedance to thermal conductance. The next thing we talked about were impurities and defects, and we rationalized sort of a way to think about them as being distributed throughout the material. So these defects could be point defects, it typically are. They could also be grain boundaries. And so here we're most interested in just the number density of these defects. That's that lowercase n subscript I. And if we look at this then as sort of a tube of transport of length capital L, we can then characterize a mean free path by knowing the density, the number concentration of defects, and the length of this tube. And in fact, the lengths cancel out. We end up with a really nice result that the mean free path goes as the cross-sectional area of this cylinder. That's pi d squared, right? Or the inverse of that. So the smaller it is, of course, the larger the mean free path. And so this defect, D, in this case, is sort of an effective radius of, it's an effective radius or diameter, depending on how you look at it, of the defect itself. And that turns into a nice clean scattering rate. And you can notice, and this is important, if I have a constant or uniform impurity number concentration, if I have a defect diameter that's roughly constant, meaning the same type of defect generally in the material, and a constant root velocity, which, for example, for phonons would come from a Debye approximation, then the scattering rate itself will be a constant. And that makes it, again, very easy to treat in the Landauer formulation. So then we talked about 3 phonon scattering processes. We had different types, and so there are a couple of different types that we classify as normal, which means that the momentum and the energy are conserved. In all cases, in all of these scattering events, energy needs to be conserved. But for normal processes, momentum is conserved, and because of that, there's no impedance or resistance to heat flow. However, there was another type called Umklapp or U processes in those cases, when I have 2 phonons coming together, their vector sum would actually give us a wave vector that would be outside of the first Brillouin zone, which would mean it has an impermissible wavelength. The wavelength would be too small. And so what we have to do is translate that back into the first Brillouin zone with G, the G vector. That's the reciprocal lattice vector. And when you do that, you can actually kind of turn the phonons around, and still you conserve energy. So there's some energy rules that you have to follow that can become very, very intricate. So this is a extremely complex subject, and I don't want to make it seem very easy when we look at scattering rates. But this is the physics of the process is captured by these normal and Umklapp processes. We also learned that the normal process does not impede heat flow, so it is not included in that mean free path or scattering rate that goes directly into the conductance integral. What we end up doing for all of these different scattering types that impede heat flow is we sum them if we can, and that means and the times that we can are only when the scattering processes are independent of each other. That means that one scattering process does not cause another one to become more or less relevant or more or less probable. So when we have that case, then the scattering rates are additive, and this is called Matheson's rule. And this is a very, very common assumption. And you'll also find that the scattering rates are often used in engineering approximations as adjustable parameters to fit experimental data. Now, scattering itself can be very complicated. Again, I'll repeat, I do not want to trivialize it in any way. I will just say that if we took a simple example where we had a one-dimensional problem, a one-dimensional conductor with M, that means the number of modes equals to 1, and we include 2 types of scattering processes. So here we had the first term is this B omega squared T. That would be representative of a power law type of scattering that might be a decent model for Umklapp scattering. And then C is a constant scattering rate. So again, we're summing these scattering rates of different types. That's Matheson's rule. C would be like an imperfection, a defect scattering rate. And again, the first term, that omega squared T times B, that would be like a U process. And what we would find is that for very low temperatures, the constant scattering rate dominates. And that's because we're sort of at very low temperatures, the frequencies are very low. So this frequency squared dependence would make the first term in the scattering rate very small, as would temperature itself. And so essentially those types of scattering events are frozen out, and we just have a constant scattering rate, which means that the temperature dependence of the thermal conductivity it inherits the temperature dependence of the specific heat. You can kind of think back to our kinetic theory for that. And in this problem, we have a one-dimensional problem, so it's a t to the power 1 dependence. Then what happens is we get into this middle range of temperatures, and in this case, it's still pretty low. It's 10 degrees Kelvin, but then the thermal conductivity begins to plateau as this frequency-dependent scattering rate starts to take over. At the same time, the specific heat will start to plateau. That's the law of Dulong and Petit, if you remember. And so the two things are happening that causes the thermal conductivity to decrease. So this is something that you'll see. This is the profile for thermal conductivity that's very typical of real materials whose thermal conductivity is dominated by phonons. Then we took a pretty big step, and we started to look at interfacial heat transfer. So in this case, what we were looking at is not a number of scattering events in the device, but an interface in which the number of modes on one side differs from the number of modes on the other. And so we ended up with having to deal with that in a new way. It wasn't quite as easy as the simple scattering model. And we had to deal with this number of modes difference, and especially with respect to different types of interfaces. So the first thing we looked at was the acoustic mismatch model. So in the acoustic mismatch model, it's sort of like the perfect interface, as perfect in the sense that we have crystalline continuity and planarity between the two phases. There's no roughness, in other words. And in that case, you can treat the interfacial transport in much the same way that people deal with acoustic waves. Those are typically long waves, and so even a real rough surface to you and me would look fairly smooth to long acoustic waves. And so for this acoustic mismatch model, there's a well-established theory, and we went through part of it using continuum theory of a string under tension with two different mass densities. But we found that this concept of acoustic impedance, that Z, becomes important. It's the product of mass density and velocity. And in that case, we found that the transmission function, or the transmission coefficient, that's that script T, equals the transmissivity T12 and T21. Those are the two transmissivities from side 1 to side 2 and side 2 to side 1. Those could both be expressed simply in terms of the acoustic impedances of the two media. That was for a one-dimensional problem. When we went to 3 dimensions, like so often, life gets a lot more difficult, and we have a direction dependence to the transmissivity. That's the lowercase t12 and t21. And what we end up having to do is to integrate over the spatial incident angles. And that becomes very difficult. We didn't actually go through an example, but there is a homework problem that's related to that approach. The second kind of interface model, it's a little bit easier to understand. What we did was we applied the principle of detailed balance, which simply says that if the temperature of my two reservoirs is the same, then I can have no net heat flow between the reservoirs through the device. And when we apply that principle, a really neat result came out. That was that the transmissivity, that's T12, is equal to the ratio of the number of modes on the opposite side. So if I'm going from side 1 to side 2, that's the total number of modes at that frequency on the side 2, divided by the total number of modes on both sides. So it's sort of the fraction of modes on the other side. That gives us the transmissivity. And that, I think, makes some intuitive sense. Really what's happening, by the way, in this model is that we're assuming that the carriers go to the interface and they're scattered around because the interface is rough, and they lose memory of not only their direction but also the branch that they were on, and then they move out. We have to conserve energy, of course, and so then they move out somewhat randomly from the interface, but according to, again, this sort of mode counting rule that we established here. And then the last topic was thermionic emission. That was lecture 5 for this week. I wanted to make sure that the electrical engineers didn't feel neglected in the course, and also this is a really fun and interesting topic. But thermionic emission is the emission of electrons out of a material. It's sort of like the boiling of electrons from a material. So you might wonder, well, why do we need to boil anything out? Well, the electrons tend to stay inside of metals, certainly at normal temperatures, because there's this thing called the work function, an energy barrier at the surface that keeps them inside. But if we heat the material enough, then we can start to excite the electrons enough, or a significant number of electrons, according to the Fermi-Dirac distribution, so that some of them emit out of the material, and that's called thermionic emission. And we came up with a theory. In this case, this was for the electrical current density J. So that's why if you look at this bottom integral, we don't have an energy weighting to it. There's no E minus mu, which we had when we were looking at heat transfer. There's also not any reverse flow. So there's not a T2 term in this equation, because we're assuming that the side 2 is so cold that nothing is emitting backwards in this device, although you could easily add that. And what we found is that we could predict the energy distribution. And so here we're showing the electron energy distribution for a material with a work function of 4.5, roughly 4.5, 4.6 electron volts. The dashed line is the theory. So this is called the electron energy distribution. It's really just the integrand of our current density integral. And you can see that theory and experiment match very well. And so this is pretty powerful in terms of being able to make some measurements and think about how energy is distributed in the electron field. And thermionic electron sources are useful in general for electron sources on, for example, on scanning electron microscopes, but also thermionic emission can be used in energy conversion processes. It's also important just for kind of plain old electronic transport and understanding how current can leak. If I have a device that's getting too hot, how current can leak over a solid state barrier, in which case it's not vacuum emission, but it would be an internal solid state thermionic event. All right, well, that's all I have for the class. I had a great time, and thanks so much for your participation. It's been a wonderful treat. I've been a little bit tired, but had a lot of fun, and hope you did too. Thanks.
Oh, Tim. I know class is glad this semester is over. I guess you are too. Let's go have some fun.
All right, let's go.